We're going to continue with chapter 2 into part 2 here. And in this section, we're going to do a little bit of math. So get out your calculators or open it up on your laptop so you can kind of follow along with what I'm doing. There are calculators, obviously, built into your laptop. And if you go to View, you can actually choose the scientific one. You don't need it for this chapter, but for other ones, it'll come in handy. So mine's always in scientific, if you'll notice, because just in case. I'm going to stick that up here because I may need it in a minute. But what I'm going to do first is I'm going to look at derived units. And a derived unit is a unit that's a combination of SI units. So an example of that is volume. Volume is the amount of space occupied by an object. Oh, there goes my calculator. That's all right. I'll bring it up when I need it. It's the amount of space occupied by an object. And the reason it's derived is because it's 3 lengths multiplied together. Right? It's length of the object times the width of the object times the height of the object. That's for a cube or one of those. I mean, obviously the volume of a sphere is different than the volume of a cylinder, but basically you're going to need length at some point in there because usually volumes measurements are something cubed, like centimeters cubed, inches cubed. So it's a derived amount. It's not going to be an SI base unit because you need to use multiple SI base units to find it. Another way to find volume, though, which we'll learn in lab, where you already did the lab, is water displacement. And that's the measuring of volume of an irregular shaped object, like a rock, or something that isn't just, square, or a sphere, or a cylinder. So a rock would be a good example. We use the penny and the marble. Other irregular shaped objects can be for anything that you just can't look at and figure out. So what happens with water displacement is, well, think about it. If you fill up a bathtub all the way to the tip top, and then you get in it, what's going to happen? Yeah, the water's going to go all over the place. You have displaced that water. You kicked it out of the tub because you have volume. Okay, that's what's going on with water displacement. Is what you do is you fill a graduated cylinder up to a certain amount. Let's say you fill a graduated cylinder. Don't mind the drawing. You're going to fill a graduated cylinder. Remember, they look kind of like this. And they have graduations. Let's say this is 0 to 100. I know, there's not enough indents. And that's 50 in the middle. And let's say you fill it with water up to the 25. Okay? And then I drop in a huge rock. And it goes from 25 all the way up to 50 once I put that big old rock in there. Okay? So what it's saying is the water was 25 milliliters of that volume. The rock is the rest. So your rock's volume is 25 milliliters. Now it only works if the density is greater than 1, because water's density is 1. Because if you try something that doesn't have a density greater than 1, it's just going to float. So water displacement is where we use a graduated cylinder. I'm just going to write it out in terms so that if you don't understand my fabulous drawing, maybe you'll understand the words. You use a graduated cylinder. You're going to fill it to a certain point and drop the object in and subtract the new volume from the old. Fill to a certain point. And I'm saying certain because it doesn't matter which one you pick. You're going to be subtracting. So whatever point you like. You fill to a certain point, drop the object in, and subtract the new volume from the old. Or the original. We're going to do that again in another lab with density. So you need water displacement to find the volume of irregular shaped objects. And the way that we used it was for what we're coming to right now, number 4, the density. And that's the ratio of mass to volume. And remember, we said that density, we love it, just like we love chemistry. That's why it gets this wonderful heart. But density is actually our broken heart. And that just helps us remember that it's M. See, here's the M right here on the top, over V, or volume. So it's mass over volume. Mass mass is usually units of like grams. Um, volume can be milliliters, centimeters cubed, anything like that. Or it didn't want to work on that word volume, so we'll see if it's just stopped on me or not. There it goes, it's still working. All right, so here's a couple problems. I'm going to do some examples for you to follow, but we're using that equation for density. So I'm going to put it up near the top. Density equals mass over volume. So the sample of aluminum metal has a mass of 8.4. So M equals 8.4 grams. Got it. The volume of the sample is 3.1 centimeters cubed. Calculate the density. Well, and I know that density equals M over V. So it's what I'm going to do is I'm going to take my M, 8.4 grams, over my V, 3.1 centimeters cubed, and I'm going to divide. And I'm going to get 2.7. And your units, they don't cancel out, so they're both there. Grams per centimeter cubed. And that's it for density. Let's see if we can do the second one. Now, if you want, you can pause the video here, try it on your own, and then come back and check it. Or if you want to look at what I just did again, rewind and watch it again. I'm doing number 2. Diamond has a density of 3.26. So density equals 3.26 grams per centimeter cubed. What's the mass? Oh, mass here is our question, so it's a little different than the first one. The volume is 0.351. So I'm going to use the same equation. Density equals mass over volume. So my density, 3.26 grams per centimeter cubed, equals my M, that's my unknown here. You can use the term X if you like. X is better than M's. It does not matter. Over 0.351 centimeters cubed. Now to solve this, we want to get the 0.351, the volume, out of the denominator. So I'm going to multiply both sides by 0.351. And I'll get a mass of 2.7. Oh, I'm sorry. That was the answer to the above one. I'll get a mass of 1.14 grams. Okay, so I did 3.26 times 0.351. Try it in a calculator. Make sure you get the same answers as me. Don't just write what I'm doing. Try that. Number 3, a regular shaped object has a mass of 96.2 grams. The rock is placed in a graduated cylinder with 50 milliliters of water in it. The water level rises to 88. So our volume is going to be the difference of those. 88 milliliters, oops, minus, not equals, milliliters, minus 50 milliliters is 38 milliliters. They want to know the density of the rock. So I'm going to take my mass, which is 96.2 grams, over 38 milliliters. I got 2.53. Type into your calculator. Make sure you get the right answer. That's a big thing when you're listening to these. Don't just go and write down what I'm writing down. Actually be an active learner here. Actually go in, try it on your own, make sure you get the same answer. Because if you type in the calculator wrong on the test, you're still going to get it wrong. So make sure you type it into the calculator right now. All right, we're going to do temperature also with this section. We'll stop at dimensional analysis, but there's a new temperature unit. It's the SI unit for temperature. We learned it a little earlier. It's called Kelvin. K-E-L-V-I-N. It's capital because it's named after a guy's last name. Why do we need this? Well, it's what happens is when we get into chemistry and we start factoring in what temperature has to do with all these reactions and the energy and what happens on a molecular level, we multiply and we divide and we add. And the problem is if we divide by a 0 or multiply by a 0, we're done. The answer is always going to be 0 or infinity. So they have made this temperature scale that will never go to 0. That's what we have is absolute 0. Absolute 0 is 0 degrees Kelvin. Looks like okay, but it's 0 Kelvin. Now we can have 0 degrees Celsius easily. That's where water freezes. We have 0 degrees Fahrenheit easily. We've had it before, especially this past winter when it got really, really cold. So, but you can't have 0 degrees Kelvin. This is what they got really, really close to with the Big Hadron Collider. It's where they try to figure out that this is about the temperature where the Big Bang happened. So they can do it in a laboratory setting where there's lots of pressure and it's under a lot of control, but it's not something that's going to actually happen in a normal environment. Absolute 0 is so cold that all molecular motion stops. Okay, that's how cold it is, and that's not going to happen. It's not going to get cold enough that our electrons are no longer spinning, that we cannot move. Obviously, we would not survive that. Excuse me. So that's why we have 0 Kelvin. That's why we have the whole Kelvin scale. It's because we can never have a 0 in the denominator. We will never have a 0 multiplying. We're never going to have a negative number in there for temperature. So it's always going to be a positive integer for temperature. That's why we need Kelvin. Now, the conversions are super easy. You're going to love it. From Celsius to Kelvin, you take your degrees Celsius and you add 273.15, and that equals Kelvin. If you want to go and find Celsius and you're given Kelvin, you take your Kelvin, you minus 273.15, and that equals degrees Celsius. Now, these two, Fahrenheit, we're not going to use it all this year, so you do not have to commit this to memory. We're not even going to use it in practice, but just, so that you have all the facts. Degrees Fahrenheit minus 32 times 5 nines equals degrees Celsius. It's not a conversion we're going to do, so you don't have to worry about memorizing that or anything, but just for completeness, I figured I'd put it in there. Now, these next ones are converting between Celsius and Kelvin. You do have to know how to do that. So for A, if I have 320 Kelvin and I want Celsius, I'm going to take my 320 minus 273.15, and I'm going to get 47 degrees Celsius. Now, if I start with Celsius, I have 25 degrees Celsius. I'm going to add 273.15. You're going to get 298 degrees Celsius. And I'm only going as many decimal places as that first number that they gave me. That's why, oh, I'm sorry, it should be 298 Kelvin. That's why I'm stopping at just a 298. I'm not putting the 0.15. For C, I have 37 degrees Celsius. Add that to 273.15, and I get 310.0 Kelvin. Oh, 0.1, sorry. Just putting that one in my head, sorry. 0.15, so it'd be 0.2 Kelvin. So 310.2. Now, pause it. You only have 3 left. Try them on your own. See if you add and subtract correctly. And then when you come back, I'll throw up the answers. All right, here are the answers for the last 3. You have 211 Kelvin. You have negative 223 Celsius. And 436 Kelvin. Check your answers. Make sure you got it right. And that's it for this part of the video.